Hey guys, we're going to take a look at the remaining four trig graphs, tangent, cotangent, secant, and cosecant, and how they're developed, where they exist, where they don't exist, the period, all that kind of stuff. So the first one is the tangent graph, which you were actually on, I think, one of the earlier assignments asked to explore on your calculator by plugging in values. But if you think of tangent using our quotient identity here as sine over cosine, then whenever cosine of theta equals 0, you're going to be dividing by 0, which is going to result in an asymptote. So that's what you want to be thinking about when you're graphing tangent, is where is cosine 0, and when that's true, you're going to have asymptotes there. So if we look over the course of negative 2 pi to 2 pi, and where cosine is negative, we'll sketch that out. So cosine is going to look like this. So when it comes to tangent, at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2, I'm going to have asymptotes there, and that's because my cosine, I know those are the quadrantals where cosine is 0, and so tangent is not going to exist there. Outside of that, and you can play around with plugging in some values, but finding what does the tangent graph look like. If you think of this being 0 and pi over 2, this is Q1. From pi over 2 to pi here, that's Q2, this is Q3, and Q4. And a negative rotation in the unit circle, that's going to be Q4, Q3, Q2, and Q1. And what's true about tangent in all these respective quadrants? And tangent in every trig function is going to be positive in quadrant 1, and tangent is increasing from 0 to 90, or 0 to pi over 2. So it's increasing, and as it approaches the asymptote, it's going up like that. Similarly, if you were to rotate into quadrant 4 in the unit circle, you're going to get larger and larger values, negative pi over 3, negative 1, negative rad 3 over 3. As you approach the asymptote, it's going larger and larger in the negative direction. Now what's interesting is that as you then fall into quadrant 2 for tangent, tangent of 120, 150, I guess 145, 135, 150, it's getting bigger, but it's coming up from really large negative values. So what's interesting in quadrant 2 here is that you're actually headed towards 0 again, but coming up from negative infinity. And then in Q3, tangent is positive, so Q3 is going to look exactly like Q1, that positive increase. So what happens in the tangent graph, and this last one's not my best, there we go, is that you get this same shape increasing from left to right over and over again in between these asymptotes. And when you think about the period, the basic period of the tangent curve, it's pi, or 180 degrees, if you want to think of it that way. Because the period, or the basic period, is how long does it take before the graph starts repeating itself? And we knew that for cosine, I'll try and sneak that in here, right? Cosine up to this point does not start repeating itself. It's not until we get back up here that cosine continues to repeat itself, and we saw that going back this way. That it takes 2 pi for cosine and sine to repeat itself, but it only takes tangent pi or 180 degrees to start repeating itself. If we were to graph y equals tangent 2x, that 2 could be an a, is it a b, is it a h, or a k value? Well, because it's tagged up with the x, it's a b value, and it affects the period. Now, we'll keep it pretty basic with these remaining graphs, tangent, cotangent, secant, and cosecant, and not throw a lot of amplitude changes and horizontal and vertical shifts. But Mr. Nicoletti and I will give you different b's to evaluate frequencies to then change the period. Now, if you were going to graph y equals tan 2x, you may think, oh, okay, well, I could graph cosine 2x and see, again, where does cosine 2x, where does that equal 0? Because that's where my asymptotes are going to be. Now, because the frequency is 2, that means I'm going to be able to complete this graph in a shorter amount of time, in half the time. So we're going to look at negative pi to pi. But the same idea is going to exist, where if I think to myself, okay, cosine 2x also gets done in half the time. That looks like that. Therefore, I have asymptotes still at these same values. Well, they're different than before, but kind of to scale in the same place. So my graph between these asymptotes it's going to look like the graph we had earlier. Just I'm able to fit more in well, I guess the same in a shorter amount of time or more in the same amount of time, however you want to think of it. But that would be your graph of y equals tan 2x, the green pieces there. So either kind of in your mind's eye, and I'll sketch it here in just a second, or with your calculator, think to yourself and execute y equals tan of 1/2 x. What's the period? Well, for this guy, all of a sudden, I can only fit half the graph over the course of pi, or I'm going to need twice the space to fit in 1. So rather than my original graph, which existed between negative pi over 2 and pi over 2, I'm going to need twice the space. So negative pi to pi, that's where my asymptotes are going to be, and jazz it up with another color here, and we get that graph there. Hopefully that resonates with what you're able to get on the calculator. If you're in, make sure you're in radian mode to match that graph. Now the same logic is going to apply for the cotangent graph. We're just now going to ask ourselves, what the heck is sine x doing? When is it 0? So we'll sketch this in. There's sine and 2 cycles of it. Looks like that. Therefore, I have asymptotes at negative 2 pi, negative pi, 0, pi, and 2 pi for the graph of y equals cotangent of x. Because anytime sine of x is 0, cotangent of x is going to be undefined. Now again, thinking to ourselves over the course of the quadrants here, I know that cotangent is positive in quadrant 1, but it's descending as I rotate towards 90 degrees. It's going from rad 3 to 1 to rad 3 over 3, and when I get to 90, that's when cotangent is 0. So it's decreasing until I get to here. And then in quadrant 2, it's negative and still decreasing. And then we know that quadrant 1 behaves the same as quadrant 3 with respect to tangent and cotangent. So I end up with this graph here for cotangent. It looks a lot like tangent, just it's been flipped, and it has, right? Cosine over sine versus sine over cosine. But it's also been shifted, where those asymptotes don't quite match up, because all of a sudden sine's in the denominator instead of cosine. So it's shifted 90 degrees and also been flipped. Has it changed the period at all, though? No, the period is still pi, or 180 degrees if you're working in degrees. If we think to ourselves, okay, what is the period of, graph y equals cotangent of 3x and find its period? Well, we know that the period for a basic cotangent is pi. So pi over b is equal to pi over 3. That would be the period for y equals cotangent of 3x. And just to give us a quick sketch here what that would look like, since the entire period is pi over 3, there's an asymptote at 0, and we haven't moved that. And then instead of it being at pi, we had to trim it because we could fit 3 in. Therefore, this is pi over 6. And my graph is going to come down like that. Not my best, but there you go. And that's 0. So hopefully that gives you a good sense of tangent and cotangent, where they exist. Like I said, we're not going to be doing a whole lot, if any, shifting with those. Now the graphs of secant and cosecant are also related to sine and cosine, which actually makes them really easy to graph. For y equals secant of x, hopefully you're thinking to yourself, well, the only thing I know about secant, or the main thing I know about secant, is that it's related to cosine. Let's see, I'm going to give myself a little more space here. There we go. It's the reciprocal of cosine. Therefore, every time cosine is 0, y equals 1 over cosine x. Anytime cosine is 0, secant is going to be undefined. So let's say we go 1, 2, 3, 4 in both directions. So we'll go from negative 2 pi to 2 pi, negative pi. So I'm just going to sketch cosine. My scale is going to be kind of wonky here. Just hang tough. But there's 2 periods of cosine. Now we said anytime the cosine is 0, I am going to have an asymptote for y equals secant of x. And that's going to happen at negative 3 pi over 2, negative pi over 2, pi over 2, and positive 3 pi over 2. All those asymptotes exist. Where does secant exist? Well, we know a couple things. We know that when cosine is 1, secant is 1. And similarly, when cosine is negative 1, secant is also negative 1. We know that happens. So these points here actually all exist. But then as cosine decreases from left to right, so I'm going this way, secant is going to increase. And it's going to approach that asymptote and therefore increase in an infinite manner that way. The opposite is true in these quadrants over here. I guess this is quadrants 2 and 3. We have graphs that have these what look like negative kind of parabolic branches. And I'll just throw half of it over here because that's all I have on the sides. But that would be the solid blue components of that graph are the graph of secant, y equals secant of x. The dotted line is just your frame of reference to get the asymptotes in place, and you're scaling for where they equal 1. Otherwise, they go up and down to infinity. We'll do the same thing for cosecant, and I'll have to maybe sneak that graph down here for number 9. Just throw that together. Now I have a little more space. 1, 2, 3, and 4. 1, 2, 3, and 4. Now, if I'm talking about y equals cosecant, I'm actually really interested in what sine is doing. Y equals 1 over sine of x. So, my graph of sine is going to look like that, and every time sine equals 0, my cosecant graph is not going to exist. So the asymptotes are actually in the same place as the cotangent graph. And just like secant and cosine, cosecant and sine have these points where they are equal. Negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. They all equal 1. And we're going to have this branch situation again. It's going to look a lot like the secant graph. Again, it's just been shifted 90 degrees for pi over 2. But again, the solid part is the graph of, in this case, secant. The dotted line for sine just gives you where the asymptotes and where does it equal 1 for y. Lastly, just for question 10 here, how would changing the period affect anything for secant 2x and cosecant 2x? You would say it's half the period, or you could say 2 times the frequency over the same period. So I guess that's one thing to mention, is that the period for these two graphs is the same as sine and cosine. 2 pi over b, because it took 2 pi for the picture to repeat what it was doing. Right? Just this branch here, as I go down here to this one, the graph hasn't repeated yet. It's not until I start here again that I've repeated what I started over here. So this would constitute the one period, which is 2 pi in length. So half the period or twice the frequency for 2x and for secant and cosecant. And then if you were to say do secant a quarter x, you could say that that's going to be 4 times the period. Or, it should be or. Let's try that again. Or 1/4 the frequency. There. So hopefully you've got a good sense now of the relationship of your sine and cosine, which you're hopefully very familiar with, and its relationship to secant and cosecant, as well as tangent and cotangent. Again, the big takeaways are that tangent and cotangent are 90 degrees shifted, but also then flipped vertically because of the sine, cosine, sine relationship, tangent and cotangent, reciprocal identities. The period for tangent and cotangent is pi. And then for secant and cosecant, yeah, they look the same. They're shifted 90 degrees or pi over 2, but their periods are 2 pi. Take a look at the rest of the problems, and good luck on the homework. Come back to class with any questions you might have. Thanks, guys.